Okay, a little more on bit flags, flag bits and decision making. Because status flags are also called conditional flags, there are instructions that will make a conditional jump or a branch based on the status of the flag. Okay, we've got a little table here, provides a list of those that show the action taken given by an instruction. So these are some instructions that we will encounter as we move through the course. You can see that in each case we have a branch if a carry is set, if a Z is set, an N or an OV. Okay, so keep these in mind. We're going to see these conditional branches come up. So the next section that we look at is the Pic Data Format and something called Directives. In this section, we'll look at widely used data formats and directives supported by the PIC assembler. The PIC microcontroller has only one type of data. Okay, we've said this before. You'll probably hear it again and again. That's 8 bits. And the size of each register is also 8 bits. It's the job of the programmer to break down larger than 8 bits, 00 hex to FF hex, or 0 to 255 in decimal. So you'll see these values. We bounce back and forth between binary, hex, and decimal throughout this class and throughout this presentations. If they're to be processed by the CPU. For example, if we look at how to process data larger than 8 bits, we're going to encounter that as we move along. The data types used by the PIC can be positive or negative. So now we start getting into these signed data values that were alluded to earlier. A discussion of signed numbers is also given later on in the text. The bit addressable data will also be looked at. There are 4 ways to represent a byte of data in the PIC controller, okay, by the assembler. The numbers can be hex, binary, decimal, or even in Ascii format. So let's take a look at first hex numbers. There are 4 ways to show hex numbers. Okay, and if you look at, we've encountered some of these and you probably said, well, why doesn't that look like what we saw before? So the first one, we can use a little h or a capital H right after the number, like in this move literal statement, 99H. We know that it's a location. It's actually a value that we're moving in this case of 99 hex to the working register. Number 2, we can put a 0x or a 0 capital X, either one, in front of the number. So in this case where we have, again, a move literal W, we have 0x99. It's the same as step 1, 99 hex. It's just lots of ways that programmers use when they're writing code, what they get used to and what they're most comfortable with. 3, put nothing in front or in back of the number like this move LW99. And we've seen that before too. It's like, okay, is that 99 a hex number or what is it? Okay, in every case, the hex, it's a hex numbered location or a literal value hex number. And 4, put an H in front of the number, but with the single quotes around the number like this move LW, H, single quote, 99, close single quote. We use all 4 of these methods because many application notes are out there that use some or all of them to get the job done. Notice that some PIC assemblers might give you a warning but no error when you use 99H because the assembler already knows that the data is in hex and there's no need to remind it again. Okay, so we'll see as we move along whether or not MP Lab does that. We do that simply to remind ourselves, and it's a good reminder, when we do coding in assembly. Now let's look at some examples here. Okay, we're going to take a look at an example of code move LW 25. We know that that is telling us to move the hex value of 25. So you notice it had no other value around it, no hex, no H, no nothing. The next one, add LW 0 by L by 1 1. Again, we know that in the register, the working register, it had 25 already there from the previous step. We're adding an 11 hex to the existing 25 hex. We now have 36 hex in the working register. The next one, using the next example, add LW 12 hex. So to that 36 we already had, we're going to add 12 more to it. Now we have a hex 48. Now using the next format, add LWH with the single quotes around it, 2A. So we're going to take 48H that's already in the working register, we're going to add 2A to it, and we end up now with a accumulated value of 72 hex. And then finally add LW2CH. Working register had 72, we're going to add 2C to it, and now we have 9EH. Okay, notice that the following are invalid. Move LW E5H, invalid because it must have a move LW 0 E5H. Add LW C6, again, invalid because it must have the leading 0 C6 on there as well. So in these instructions, if the value starts with the hex digits of A through F, then it must be preceded with a 0. So since it started with an E, it started with a C, you had to put a 0 in front of it. It's just the syntax rules for assembly language. Let's look at the same thing for binary. There is only one way to represent binary numbers in a PIC assembler, and it's as follows. Okay, although we had more for the hex, for binary we've only got one. So let's look at the example. Move LW B single quote 1001 1001 single quote is telling you to move into the working register that value or a 99 in hex. The lowercase b would work instead of the uppercase b. Note that that this quote is the single key quote. Okay, this is different from other assemblers such as the 8051 or the X86 values, and here are a couple of examples. Move LW, it's telling it it's a binary number, open a single quote, 0010 0101 adds a hex value of 25 into the working register. Add literal value into the working register, binary number 0001 0001. Okay, so we're going to add that value to the 25 that's already there, and 11H, which gives us 36H. For binary or for decimal, there are two ways to represent decimal numbers in a PIC assembler. Okay, let's look at this. The example line given in decimal, we have a move a literal value into the working register, D, telling us it's expecting to see a decimal number, single quote, 12, close single quote. The working register sees a binary or a hex 0000 or 1100 or a 0C in hex. The lowercase d will also work. This is different from other assemblers, again, the 8051 and the X86s. In those assemblers, to indicate decimal numbers, we simply use the decimal value, nothing before or after. While using the PIC assembler, 12 is the default for hex numbers. Here are some examples of how to use it. Okay, so in this case, we had a move literal value into the working register, decimal 37. In the working register, that is a value of 25 in hex, 37 in decimal, 25 in hex. It's funny, on some of these things you'll get used to seeing them and immediately know what that value is without having to do a bunch of converting. Adding then a literal value of decimal 17, since 17 is a value we're going to add to 37 in the working register, we get a 54, where 54 in decimal is a 36. The other way to represent decimal numbers is to use a dot value. In this case, we have a literal value moving to the working register, dot 12. In the working register, it sees a 00001100, which is equal to 0C in hex, or a 12 in the decimal. Lastly, Ascii. To represent Ascii data in a PIC assembler, we use the letter A as our example. So we're going to move literally a value into the working register, A for Ascii, to, single quote, enclosed in single quotes. The working register then sees 0011, 0010, or a 32 in hex. Okay, and you'd have to look at the Ascii. It's telling us to look in the. We'd have to look in the in an index to see that a 32 in hex is a code value for an Ascii 2. The lowercase will also work, so you can use a lowercase a. This is different from other assemblers. Again, the single quotes are used for single Ascii characters. Double quotes are used for a string. Okay, so in this case, move LW A9 loads a working register value, the hex equivalent to a 9 in Ascii, 39H, which is the hex number for Ascii 9. Add a value of 1 to it. The working register gets 39 plus 31, because that's the hex equivalent, which gives us a hex of 70. 31 hex is for an Ascii 1. And then finally, move LW9, the working register 39, another way for Ascii. So we define Ascii strings later on. We'll see that it has more than one character. We will use the defined byte, something called a DB, a defined byte directive, that we will see later on in our presentations. So the next section we will look at is something called the directives, in this case the assembler directives.